Even I am also trying, sir, to shift to engineering, but I
Okay,
presently no. In past 11 years, I'm working in the same college. I'm just
okay,
still on the verge to shift.
okay.
Switch to engineering. Yes. Yeah, that's it.
You did MSc, BSc, MSc, and
Yes, yes.
then PhD. Okay.
Yeah, PhD was bit gap due to family commitment. So just 2023, I was awarded doctorate.
Ah,
So after that, still because I did from Presidency University, where presently I work in Presidency College in film management.
okay, okay,
Film management has established university in the year 2013 or I think 2015. So
okay, okay.
2020 I joined for our PhD. I was waiting for them for promotion, but question mark as many things are there. Yeah, that's it. Thank you.
Okay. What was your PhD on? Uh,
Sorry?
what was your topic of PhD?
Viscoelastic, ferromagnetic viscoelastic fluid,
Oh,
saturated in porous medium.
okay. In our lab also, like some people work on this. Okay, so this week uh, we had learned about mainly two things. One is regression, and the other part is interpolation. So in regression, uh, we can have either linear regression, we can also have non-linear regression. So in regression, what we do is, so let's say we conduct some experiment. Um, let's say this is just like a speed of vehicle versus time. We conduct some experiment like this, and we collect some data. Let's say at t is equals to 0, uh, at t is equals to 0, the vehicle is like at rest. So this is the this is the displacement of vehicle. Or you can also like take velocity or regulation, whatever. And this is time, the time axis. Say this is T1, T2, and T3, T4, T5, T6. And let's say this is D1, D2, D3, D4, something. So, so whenever we measure something in experiments, we cannot uh, like most of the times we cannot measure like continuously. Like I cannot measure uh, the distance. Like if I have some measuring equipment to measure something, like I cannot measure it continuously. Like today we have like lot of sensors which can measure like let's say in milliseconds, like speed at 0.001 seconds, 0.002 seconds, displacement at 0.003 seconds, like that. But you cannot like, but instead of going that much low, instead of taking that much low interval also, there is an interval like 0.001 second is still there is a gap between two measurements. So like obviously sometimes like you cannot measure, like measurements are always discrete, like you cannot make continuous, like absolutely continuous measurements. There will be some interval between one measurement and uh, the next measurement. So let's say like you are measuring speed at you are measuring displacement at some time t1, and that is, let's say, some at time t1 the vehicle is at this vehicle has a displacement of d1. At time t2 the same vehicle will go to, let's say, some some other uh, some other point. So then the displacement is some d2 or something. At time t4, let's say this is displacement, and at time 3 t4, let's say this is the displacement. At time t5, this is the displacement, something like this. And at time t6, something like this. But uh, I I know that like lot of the times I know that relationship between this displacement and the time is linear. Like I know that this should be linear, but you can see that the points which I am getting here uh, are like not linear. Like this like when I join these points, it looks like some non-linear curve. But this is because like whenever we do measurements, there is some kind of error which occurs due to the sensors which we take, or like or some external factors which affect. There will be some kind of error which happens, and we cannot avoid like few things. Like in nature we cannot control everything, like there will be some lot of external factors, all these things happen. So that's why there will be some kind of error between like the real measurement and uh, me- uh, the measured thing and the real thing. So there will be always some kind of discrepancy. So that's why like you can see that this looks like a non-linear plot, but in actual scenario I know that this relationship is linear only. So that is known, like that is a known thing, that is lot of the times like you know that the relationship between two variables, like here the example is displacement and time. So we know that we assume that the relationship between the displacement and time is linear. But after measuring, I'm not getting like the points are not falling on a line. So now what we'll do is like we have to uh, ignore these errors, like and some kind, like we have to find out the properties of this line. Okay, so I have to find out the properties of this line from the given data. So the properties, when I say the properties of line is, the line will be passing, the line will be intersecting the x-axis at some point. Sorry, the y-intercept of this line is, let's say, some point. Here it is 0, or let's say here it intersects the y-axis at some point, which is v. B is the y-intercept. And this line has some slope, which is m. So the equation of this line can be given by mx plus b. Okay. So here I have to find out m and b. So I have these various points already given, like x1, y1, x2, y2, x3, y3. So I have made some measurements. Using these measurements, I have to find out this. I have to find out these values of m and b. So that is what linear regression does. So this is also like regression can also be called curve fitting because we are fitting the curve on ba- basically we are fitting the curve based on the few measurement points which we have. So because we are fitting a straight line here, this is linear regression. Like sometimes you might also have some kind of like some kind of this kind of relationship also you might have, like some uh, exponential relation or non-linear relation. Like then let's say your measurements are also not like this, they are like this. But you know that this line in real is a quadratic curve. Okay. But when you join the measurement points, like you get some kind of this curve. But you know that in reality, the relationship is quadratic. So then you say some y is equals to x square, ax square plus b. So here, using these points, the measurement points which we have, using these measurement points which we have, we can determine the values of a and b, which will give me this curve, the quadratic curve. So here this equation is non-linear. So that's why when we find out A and B here, this process may be called as non-linear regression. So, so basically we are fitting the curve. So we know the relationship between variables, like either it is linear or non-linear, and we try to find out the uh, various parameters of that curve. Like here the parameters are slope and the y-intercept. Here also this is these are the parameters A and B. So these kind of things we can do using linear regression or non-linear regression. So like if you have I can just give you a derivation like so in linear regression what we do is uh, basically we will have some kind of this curve like and like let's say this is y and this is x, and you have taken some measurements and they are like falling like this. Like obviously I have said like there will be some measurement errors. So I'll just fit some line here. So this is my y is equals to mx plus b, let's say. Okay. So now you can see this is my real, this is the actual line which has to be there, but the measurement has some error here. So which is you can say uh, and here also there is some error, and here also there is some error. So this is the real value and this is the measured value. Red dot is the measured value. Here also there is some error. Here also there is some error. Like here also there is some kind of error. So let's say we have some data points, like let's say this is xi, and uh, this is uh, let's say this is yi. Okay. So we have lot of data points like this: x1, y1, x2, y2, x3, y3. So in linear regression, like I have to make sure that like I cannot join, like I cannot make sure and just pass the line straight line. Uh, like I'll just make it thicker. Okay. So I cannot make sure that this line just passes through this point. Like if this line just passes through this point, all the errors will get all the errors like this error. Like let's say if I make sure that this line passes through this point, like this. Now you can see that this error has become zero, but these errors have become like very large. So uh, I cannot just pass. I cannot make sure that just my line passes through one point. So what is the best thing which we can do is, like, we can make sure that sum of all these errors should be like should be the minimum. Like, so if I can make sure that that condition is satisfied, then that will be the best possible curve which I can fit through uh, all these data points. So that is the best thing I can do. So, like, for each data point xi yi, we will have an residual. So residual is this. This is the error. So we will have a residual which is yi minus m. So this is my yi, not this. Okay. So the measured, this is the measured point. This is the measured y. And mxi plus b, this is my predicted predicted y, or the value of y on this line. So this is the residual. So this thing is the residual. So I can have lot of residuals for each point. I can have like for all the measurement points. I can get these residuals like y1, y2, y3. All these things I can get. So now what I can do is, like, I can take the sum of squares of these residuals. So SSE is nothing but sum of squares error, sum of squares of error. So sigma, let's say you have n points, like sigma yi minus m xi plus b square. Okay. So now if I make this minimum, like if I make this minimum, like sum of squares of all the errors is minimum, then that is the best possible line which I can fit for this data points. Okay. So if I, or like, if I want to, like, find out the minimum uh, uh, like the values of m and b for which this sum becomes minimum, what I can do, I can just do the partial differentiation of this with respect to m and with respect to b. So I can do dou ssc by m, dou ssc by b is equals to minus 2 into sigma 1 into m, and yi minus m xi plus b is equals to 0. So if this becomes 0, then I can say that either it is the sum of squared errors is maximum or minimum. Like, I'm just finding out the stationary point. Now if I just like, simplify this, like 2 can be sent to that side, like, and it will be just becoming 0, and this is just sigma yi x, and this you can just make n into b. Sigma y 1 to n, b is nothing but nb, and this is minus also. Yeah. And now if I do this simplification by sending things to right hand side and left hand side, all these things, I'll get the value of b, m into sigma xi. So this is the value of b for which this sum of squared error of error uh, will become minimum. Similarly, I want to find out the value of m also. So I have to make sure that this sum of squared errors should be minimum with respect to m also. So that's why I'll again do this partial differentiation with respect to m, and I'll make sure I'll have to make sure that this will become 0. So now I will have 1 to n, uh, yi mi xi plus b, and in addition to this, I'll also have xi. So this I have to make 0 again. Now again, after you simplify it, like b we have already got, and I have to substitute this b here. And after you do all the simplifications, like I am not doing all the steps, I can get this m value as n into, like I won't write, like you just assume that sigma is 1 to n, xi yi minus sigma xi into sigma yi by n into sigma xi square minus sigma xi square. So now by using this both these formulas, I can just substitute what is sigma yi, sigma xi. Sigma yi and sigma xi are nothing but the measurements value. Sigma measurement values, all the sum of measurement values, like whatever there are the measurement values. Like you will have some values like this: x1, x2, x3, x1, x2, x3, y1, y2, y3, right? So you have to do this, like sigma xi is sigma x1 plus x2 plus x3. Sigma yi is y1 plus y2 plus y3. Sigma xi yi is nothing but x1 y1 x2 y x1 y1 plus x2 y2 plus x3 y3. So like that, and sigma x square is nothing but x1 square plus x2 square plus x3. So by taking all these things, I can just simply get the value of m and d for which this sum of squared errors becomes minimum. So that is the best possible line I can fit such that all the errors, like will be minimum. Like this is the best possible fit I can make for the given measurement points. So for linear regression. So this is one thing. So okay. Also, what is another thing which we can do is, like, instead of taking this formula and doing all these things, like we can also go you can also take matrix formula. Like let's say you have some uh, this y is equals to something like uh, a naught plus a1 x square, like this. So, and you will have some data points like this: x1, x2, x3. Sorry, not x square, like a naught plus a1x. Okay, and we have to find out the value of a naught and a1. So I know that this data x1, y1, x2, x1, y1, x2, x2, y2, x3, y3 has a linear relationship, and I want to find out the relationship and get these values of parameters a naught and a1. So a naught is nothing but the y-intercept, and a1 is nothing but the slope here. So here what I can also do is, like, I can take all these points. For all these points, like I'll have uh, a naught plus a1. Like you will have some, like first, like for the first measurement points, for the first measurement point, you will have some value, right? So that is x1. and corresponding y1, the value will be y1 here. Okay, this is the value. Okay, a naught plus a2 plus x2, the value is uh, a naught plus a2 sorry, this is also a1 only. A naught plus a1 plus x3 is equals to y. Now what I can do, I can take out a naught and a1 like this out, like I can take a naught and a1 like this. Yeah. So now you can see, right? So if I multiply this, I'll get this. So if I multiply both these things, I'll get this. So I have just decomposed this matrix into two matrices. Okay. So this matrix has uh, a column of ones and column of the uh, x x points of the data. So, or you can say independent uh, points of independent variables, points of independent variables in the data, which is x1, x2, and x3. Okay, and this is the matrix which has y values of the data. So these are the measured y values. Okay. Now I want to find out a naught and a1. So now you can see that let's say this matrix is, I'll just take it as x, and this matrix I'll take it as a, and this matrix I'll take it as a vector y. Okay. Now you can see that this matrix has 3 rows and 2 columns, and this matrix has 2 rows and 1 column, and this matrix has 3 rows and 1 column. Okay. I can write it here also. Okay. Now I have to find out the value of a, right? So a naught and a1 I have to find out. Earlier it was m and v, like I'm just changing the notation to a naught and a1 because you have to understand, like change of notation doesn't make sense. Like m and v, a naught and a1, like you can take alpha naught, alpha 1, whatever it is. So if I have a square matrix like this, let's say ax is equals to b, where a1 a is equals to a has side of 2 cross 2, and this is 2 cross 1, and this is 2 cross 1. Like I can just invert this and I can find out the value of x. But here you can see that I cannot invert this because this is a rectangular matrix. So I cannot simply invert it. So what a workaround I can do is, like I will just take x transpose and multiply x transpose on both sides. Okay. I'll multiply with x transpose on both sides. Okay. Now you can see that this is a 2 cross 3 matrix. This is a 3 cross 2 matrix. And this is 2 cross 1. And this is a 2 cross 3. And this is a 3 cross 1. So now you can see that this matrix has become 2 cross 2 matrix. So x transpose x has become a square matrix. So simply I can just invert this x transpose x matrix because this has become a square matrix now. So A is equals to x transpose x inverse into x transpose into y. So now if you do this, you can get the values of a naught and a1. So this will also give the same result as this method, like earlier method. But this is a more efficient method because we are involving matrices. Like whenever we do programming, matrices will save us a lot of time, and matrices, matrix calculations have a lot of matrix calculations are like very uh, like programming is like uh, the main pillar of numerical computing is like linear algebra. So uh, any operations we do matrices like will save us a lot of computational power and all those things. So that's why this is a very efficient method. And also, like you can also make sure that like if you have even like let's say more than three variables, linear in more than two variables. This is linear in just one variable. Like you can also have linear in two variables like a naught x a1x plus a2y and a3, sorry, already y is there. So a3 a2z and a3w. So this this y is linear in x, z and y. So like this will be easier method compared to like using this messy thing. Like again you have to do like here you have just like we just did with respect to b and m. Again we have to do some again some other partial differentiation we have to do, and like you will get some complicated formula, all those things. So instead of doing this, I can just take this matrix method to determine the parameters a1 a2 a0 a1 a2, and like you just have to get the inverse of this matrix and multiply with the transpose, and you have to again multiply it with y, you will get the value of a0, all the values of parameters. So this is what we do in linear regression. Okay. So in nonlinear regression, like nonlinear regression, so let's say you have some uh, you have some relationship like this. Y is equals to a naught plus a1 x plus a2 x square, something like this. Like this is a quadratic uh, quadratic curve. Like you will get a quadratic relationship or quadratic curve. So relationship between x and y is quadratic relationship. Earlier it was a linear relationship. So your curve will be something like this. Okay. So here what we can do is like we can take the error. So this is the measured y point minus the estimated y point using the relationship. So somehow if I can make these errors again, like sum of squared of these errors again as uh, minimum, I can get the values of a naught, a1 and a2. So this like obviously we cannot do like this. So what we can use for that is like MATLAB has inbuilt functions, like we can use nonlinear least square, uh, different kinds of functions are there. So for that, like we can use those things. So that is a workaround. Like we can also do this thing also, but using the nonlinear least square inbuilt MATLAB function will be a better kind of procedure for nonlinear regression. Okay. So this was about regression. So and also we had interpolation in this module. So interpolation is like there are few measurements you made, and you are sure that all this like you are sure that the curve will pass through all these points, like it has to pass through all these points, and now you have to find out value between like you have measured like this point, this point, this point, this point, this point. Now you have to estimate some value in between these measurements. Like at this point you want to, let's say at x1 you want to find out what will be the value of y based on the already measurements made. Like you have not measured it, but you want to estimate it. you want to estimate x2. So then we will use interpolation. So this is called interpolation. Interpolation means uh, finding out the missing values, or like finding out the values in between the measurements. So like you cannot go beyond this. You cannot go and estimate beyond this. This will be again called as extrapolation. So interpolation is in between the measurements. So this is extrapolation. So in for interpolation we have like numerical techniques are there. Like we won't go into those, like Newton's divided Newton codes formula, all these things. Like if you want to learn more about this interpolation techniques, you can go to the computational techniques course taken by Professor Niket Kaisar itself on NPTEL, and you can learn more about them. But here we will use the spline function
Excuse me, sir.
directly. Teach it, yeah.
Can you again repeat the name of the professor?
Niket Kaisare, like the
Okay.
one who is taking this course.
Okay, sir. Fine, sir. Thank you.
You can directly search on YouTube. I think you can get that. MATLAB computational techniques. I'll just show you. Uh,
Sir, you can carry on. I know that because no, what happened when you're saying no, I just missed the professor name. Please carry on. I
okay.
such things I know. Thank you, sir.
Okay. Okay. So here we have some examples which were discussed in the class. So here we have these points. Okay. So these are the measurements made. So this is the independent variable, which is the like the points on the x-axis. Uh, these are the measurements, various measurements made at uh, x is equals to 0.8. One, like when x is equals to 0.8, the y value measurement of y was 0.69. When x was 1.4, the measurement of y was 1.0. Like that, like we have collected like these many measurements, 1, 2, 3, 4, 5, 6. So these are the number of measurements. Like we have made 6 measurements. From this, like we know that relationship between x and y is linear. So we want to find out the best possible fit, linear fit for this data points. So meaning we have to find out the value of m and b. Like mx, like m is the slope and b is the uh, uh, y-intercept. So so for that we will use the matrix method, which we already saw. So here n is nothing but length of x, which is nothing but the number of data points. So as we saw, x is the matrix which will have columns of one. Like number of measurements are like you will have we will have a columns of we will have a column of ones, like because here the length of the measurements is 6, we will have 6 ones in the first column, and in the second column we'll have all the values of x. So this is nothing but x1, x2, x3, x4, x5, x6. So this is my x matrix, and y matrix is nothing but the measurements, like dependent variable vector. So these are the measurements which we took for some quantity. Y can be displacement or velocity or whatever it might. So and now we will have this x transpose into x inverse. So x transpose x inverse into x transpose into y. So this will give me the value of phi. Phi is nothing but a naught and a1, or m and b, like whatever it can be. Now, after getting the values of slope and the y-intercept, I'll plot these values of x and y, like, and also I'll plot the values of the I'll also plot the curve which we have got here. Like, so we know, like we will plot the curve from 0.5 to 5. Like this is the range of x from for which we will plot, and this is the Phi 1 is nothing but the y-intercept, and phi 2 is nothing but my slope. Okay. So into like m into nothing but this is x, right? So m into x. Like I'll multiply this phi 2 for all the values of x, and I'll plot it. So let's say if I just evaluate it up to this point, MATLAB is taking some time. Yeah. Now you can see that this is the uh, red line which we have uh, plotted, and you can see that like this is making sure that all the errors are minimum. Like if I take any other line, then the sum of square of errors will become uh, like will increase. This is the best possible line which I can fit through the given data points. So this is the red line which we have plotted. Okay. Like similarly, we can also use this instead of taking this like you doing all these things. There is also a MATLAB function which is LSQ
Yes,
square
sir.
per fit. Yeah, yeah.
Sure, that in the plot and in the above section,
Hmm.
this linear regression,
Yeah.
that 0.55, is it
Hmm.
just 2 point or it is infinitely many points?
No, no, infinitely many points. Like it will take a range of numbers between 0.5 and 5.
Because usually previously when we learned about matrices, within
Hmm.
the rectangle box, whatever we give
Yeah,
two
yeah,
numbers, it will
yeah,
only
yeah,
two numbers, no?
yeah, yeah, yeah. But here, like you can 0.5. Like in plots, I think you can give it. Like here, this will take it as like only two. Like it will take it as a vector, row vector. But here, when you give something like this in the plot, it will take it as range. Can take like this. Uh, yeah. No, I think it has just taking 2 points, I guess. Yeah, you are right. This is just 2 points. 0.5 and 5.
So it means it's only connecting two endpoints, and as we
Two
know, only
endpoints.
one line can be
Yeah.
drawn to 2 points.
No, no. Like you can also like use. I think you can also use like take some say 0.1. Even like if you use this also, you will get a line. Like it will just plot lines. It will just all these points, and it will join all these points with lines. Okay. Forget this. Yeah. You'll get the same thing. Now I have taken, right? Like a lot of points we have taken. So all these points you can see here 2.7, 2.8, from 0.5, 0.6, 0.7. Like I have taken a lot more points. Like earlier there were only 2 points. Like here I have taken a range of points.
So
So
we are
from
going to
zero
get the
point 0.5.
same line.
Hmm?
So we are going to get the same line only.
Yeah, yeah, because this equation is a equation of straight line, right?
Uh-huh.
This is nothing but a naught
The
plus.
same line, and so it's
Yeah.
going to depend on only 2 points: end point and the starting point.
Earlier it was end point and starting point. Now it is like in between points also I have taken like 0.5, 0.6, 0.7, 0.8 up to 5. Like
Okay.
now, and also the second thing which we can do is like instead of all doing all this hard work, like taking x, y, and defining this matrix, again taking the inverse, multiplying, and all this, MATLAB has this inbuilt function which is LXQ per fit, which we can use. So for that, first we have defined this function. Uh, Mylin example, this is the function which we have defined. So this is nothing but the evaluation of linear function which will get like, so we will have some phi 1 phi 2 like, which is nothing but a naught, like a naught plus a 1 into x. So for all the x data which we give, this function will give the values of this function fl for all the values of x data which will give. So phi will be there, like phi is nothing but like some value of phi, like you can give some initial value of phi for, which is nothing but like m and d, some initial value you can give, and also x data which you can give, and this fl will give the evaluation of that function. And lsq curve fit can be used like this, like this is the syntax for it. First, you have to define the variables, which is x and x data. So instead of x, x might be confusing. Like I'll use p here. So p is nothing but my uh, the values of these things, the value of the parameters, like vectors having the parameters like phi 1 and phi 2, phi 1 and phi 2. Instead of phi, I'm writing p here. And I'll give uh, these initial values, like I'll assume these are my values, like initialize, like in order to use my this function lsq curve fit, I have to initialize with some values, like one here I am assuming it as 1 and 1, and then I'll give the values of measurements, which is nothing but x and y. So these are the values of measurements x and y. Then this lsq curve fit function will give me the value of uh, parameters m and t. Here, nothing but phi 1 and phi 2. So here already I have used phi, that's why we are using phi 1, like phi 1 here as the variable name. So it will give me two values, which is phi 1 of 1 and phi 2 of 2. Using those two values, I can fit a curve like which is a straight line. And I can also plot the same thing, like I can also plot the same line. So if I plot this, like earlier thing, and also the uh, solution which we got through the LSQ curve fit, if we plot the both the curves, we have to get the same line, because both the things will give both the things are doing the same thing, like this LSQ curve fit and also whatever the manual thing which we have done are the same thing. So it doesn't make a difference, like we so that's why these two lines should match, like these two lines should fall on each other, like these should lines should coincide, like the red line is which we had plotted using the manual method, and the green line is which we had plotted through this lsq fit function. So this is a much simpler way, like you can say. So that's what, like we can make our life easier using this LSQ perfect.
Excuse me, sir.
Yeah,
One doubt I had, if we just compare with our previous week class,
yeah,
where we used to use, let us say, some function, but we used to always equate to some within rectangle bracket x value means okay, time. We had last
ah,
time time, and there were
yeah,
two variable y1 y2.
yeah,
So
yeah,
we used to have a t solve y solve within the
yeah, yeah.
bracket rectangle bracket is equal to the function whichever we are using. When
Hmm,
we used to go for plot,
hmm.
we used to give that t and y followed
Yeah,
by
yeah,
the other instruction, etc. But
yeah,
here
yeah.
in line number 21, the
Hmm,
doubt is we have just said plot, but
hmm.
we have first given the range.
No, this is not range. These are two values only. These are two
Two values
values.
of
These are two values of x. Like I can just like instead of doing this, I can just give this x measured or xs. I'll say xs. Okay. So I'm just like xs is nothing but the values at which I am drawing the line. Okay. And this I can take it as oh yes. This again I can substitute it as xs. Okay. The same thing. Same thing will work.
thank
Here
you, sir.
I'm just taking two values of x. Okay. I can also take like this. No one like nothing will happen. Like I can also take a like lot more x values. Earlier we used only the endpoints, right? Like now I can take lot of points from 0.5 to 5 and get the same like this. This is just some confusion, I think, but yeah. Like here we have already like uh, in the plot function only we are giving the vector x and vector y. So we can avoid doing that. For better clarity, we can write like this. And then we went to this example of reaction rate. I think where is that? We just uh, PPT. Yeah. So then in the next week, sorry, in the next lecture of this module 9, so we saw this uh, estimating the parameters for Arrhenius reaction. So this is the rate of Arrhenius reaction, formula for rate of Arrhenius reaction, which is R is equals to K naught into e power minus E by RT C power n. Some looks like some complicated thing, but like we have the temperature values and we have the concentration values. And for those values, we have the rate of reactions. Like like these are the rates of reactions for this temperature and for this concentration. So temperature is there, concentration is there, and rate of reaction is there. So now we have to find out what is the value of K naught and E by R. So that is our goal. Like these are the parameters here, K naught and E by R. Okay. So now you can see that this is a nonlinear equation. So now we can convert this nonlinear relationship into linear relationship by using log function. Like I can apply log on both sides. So I'll get uh, log R is equals to log of this entire thing. I know that like log mn is equals to log m plus log n. So I can do that thing. So we will get log k naught plus log of e is nothing but again 1. So we can get uh, minus e by rt into uh, minus e by rt. So minus e by rt can be taken as like instead of so e by r is the thing which we have to estimate. So that we will assume at a1 and in the final thing like we have concentration which is nothing but n into lnc. So we'll get we'll take lnc as u and a2 is nothing but n here. So first, like we have to prepare this data. Like this has come in the form of uh, like a matrix structure. Like I have to make uh, like a nice thing. Like because like I have to make sure like for one concentration for one temperature, this is my rate of reaction. For this same concentration for this same temperature, this is my rate of reaction. So I have to prepare my data like for various combinations of C and K, for various combinations of C and T, there will be lot of reaction values. Like I have to make it like uh, a vector of C, a vector of T, and a vector of R. So I have to make my data, prepare my data like that. So I have these are the values of R which we have like 1.48, 1.67, 1.86, all these like all these values. These are the values like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So there will be 25 values. So all these 25 values are taken here. And like there are only four concentration, 1 mole, 2 mole, and 3 mole, and 4 mole. So I have these four values, and then I have five temperature values, which is 400, 400 Kelvin, 450, 500 Kelvin, and 550 Kelvin, 600 Kelvin. So five temperature values I have. Now I have to reshape this such that I want to like get like these reaction rates like whatever there are like these are for like various combinations of CNT like 1 and 400 there will be 1.48 1 and 450 1 and 450 like 1 mole and 450 there will be 1.6. So I have to make a table like that. Okay, so we will what we will do is like we will first repeat the values of C for all temperature points. Like for all temperature points means like for 400 I will for 400 I will have uh, 1 mole, 2 mole, 3 mole, and 4 mole. For 450 and I'll have 1 mole, 2 mole, 3 mole, and 4 moles like that. So I'll make a repeated matrix like if I just run this like uh, this looks like some complicated thing. Yeah, nothing complicated. So now you can see right. So this 1, 2, 3, 4 moles for this is for first temperature, and then again uh, for second temperature for 450 and the third temperature like that. We have repeated this. Like we have five temperatures, so we are repeating it for five. We are repeating it five times. So and we only want one time. So we are just taking one row. So we are taking just one column. And similarly, we have this temperature matrix. Like we can uh, reshape this temperature matrix into a column vector. So I can make it like so first I have to repeat this like for four values like for four values like of concentration I have to have uh, all the temperatures like air 400 400 400 450 450 450 like that I have to repeat it, and then after that I have to reshape this into a like 20 cross 1 matrix. So if you also run this like you will get like this, and now you can see if I run this, now you can see like this like, so we will get like something like this. So and then after that I have to prepare the data which is C and T, and there is also R. We have to combine this R with C also. So let's say if you just if we just I'll just clear this. So I'll run up to here. I'll run this up till here, and I'll plot x data minus x data comma y data, column y data comma y. So now we have, now you can see this is the magic which we have done here. Like we have made this matrix type structure into a vector kind of thing. Like for 1 mole, 400 Kelvin, this is my rate of reaction. For 2 moles, 400 Kelvin, this is my rate of reaction, which is uh, it has to be 2.5. Yeah. Okay. Okay. So the code in the lecture has some error, I guess. Whatever the code was there. For 2 moles, 400 Kelvin, we should have some this value, but we are getting something like this. Uh,
Sir,
yeah.
just I have a doubt. Just to see R, that is line number 7.
Hmm.
If you give dot,
Ah,
I don't know to what extent I'm right, but I
ah.
think if you give dot dot dot, it is the same row, no?
Yeah, yeah, same row.
But if we
This is
see
just
the,
I'm just trying to avoid writing in the same line.
but sir, when we see the table,
Hmm.
that is PPT, it is column. I think, but we have got totally 4 rows and 5 columns, no?
Yeah, yeah, yeah. But
I think that should. I don't know to what extent I'm right, but if you just see once, if you remove the dot,
oh, I think we just have to make this into a transpose.
okay,
Uh,
no, okay, fine. This is also fine.
uh,
Yeah.
no, no, this we'll figure it out. Nothing changes.
Oh, okay. No change.
There is some error here. data 20 cross 1. This is okay, but here there is some kind of error. This we don't need. Yeah, now it is good. You just have to repeat. If I take my data, where is data? Yeah, now it's fine. 2 modes, 400 is 3.2. Okay. So there was some error here. Before. Yeah, this should not have been used. So this thing reshape was not necessary. Uh, yeah. Okay. So we have got, so earlier we had only like one variable. So we have now multiple variables. Like so linear, our relationship is linear in multiple variables. So here you can see that our equation is linear in x and also u. Earlier we had only x. Here we have x and u. So now we have got this is our x. So both of these columns are x, and this is our y. Okay. So when I say x, it includes x and u. Okay. So this is multi-linear regression. So linear regression in multiple variables. So then we will do the same things, like we will uh, take this and uh,
Sir,
prepare this data. Yeah, yeah.
sir, can you just the previous code, no, which you just made correction? Can you just see
Mm,
once if you take transpose for R, are you
mm.
getting the same what the
Yeah, you will get the
alignment
same
is?
thing. You will get the same, because this is just a vector, right? Like you take whatever you take. Again, we are reshaping it. So see, this R doesn't have any like it won't cause any problems. I'll just show you. You take transpose or whatever. Even if you take etc. Yeah, same thing will get.
Yes,
No
sir. Thank
problem.
you, sir. Sir, can you just explain this? What is this REP? That is line number 16,
Mm.
17. That is what this code actually does. REPMAT, and then reshape and repmat, whatever we call it.
So this
Uh,
rep mat is nothing. This is doing. This is just repeating this matrix. How many times it has to repeat? This is 5 times. Okay. So
and one stands for
hmm,
after five. One is there, no? That stands for
after five, one is like one row. Like let's say I'll just take this and run this. I'll get this. And let's say if I use two, I'll get two rows. Can see right? Like
right.
some
So we get two columns, sir.
yeah. We get
Okay.
two columns. So I just want one column, right? So I take
And what is this reshape?
reshape. Reshape is reshape is not required actually here, but yeah, reshape is like you have some vector, right? So you can make that vector change the shape of that vector. Like earlier we had this r how do we uh, can say size, right? Size, size, size of r. Hmm. This is also not required actually. Like this is just making this matrix like uh, let's say you take R transpose, like this is the transpose. Like instead of taking this as a row vector, I am taking it as a column vector. Now what will be my size? My size is still 20 gross. No. First I have to run this. Okay. Okay. Now size of R is still 20 gross one, which too much. I'll just give an example. Let's say you have some D is equals to 1, 2, 3, something like this. So what will be the size of D? Three, three rows and one column. Now let's say you want to reshape this and you want to make this a column vector. Now what you can do is use reshape D and you can make one row and three columns and do it like this. Okay. So earlier it was a column vector. Now we are changing it into a, so this was my D. Now I'm reshaping D and converting it into a column vector. Let's say if you have same something like instead of this, a matrix like this also. Okay, now what is the size of this matrix? 2 cross, sorry, 2 cross 3. Now you want to convert this matrix as a row vector, like as a column vector. Now what you can do is reshape D as 1, 2, 3, 4, 5, 6, 6, comma 1. I want to reshape this. So if I do it like this, now you can see this matrix, which D was the matrix, right? So this matrix is, this is the matrix, earlier matrix which I gave is reshaped into a column vector. So reshape is doing. That so reshape does this. Here we don't require reshape actually. It's not necessary. Even if I take just like this, it won't be because this reshape is doing nothing here. Okay.
So this can you show that last code where you have just explained the reshape. I'll just take a pic of that. So this was the D matrix given.
Mm.
Then I can just show that reshape.
This is the reshape. Like
Uh, can just scroll a bit up because no, your name is there. No, it is overlapping that.
my
Just a
name is
bit.
what?
Yeah, the Syed Shabir Ahmad is presenting that is coming now.
Ah,
That
okay.
is okay. Okay.
Now you can see.
Yeah, just take it bit. Yeah, yes, sir. Last one, last. Yes, enough. This one. Enough.
Okay.
Thank you.
Okay. So reshape is nothing but reshaping the matrix. Like you want to change the size of the matrix. Like you will rearrange rows, columns, and make uh, something. So now I have this X data. So because like I am taking log and doing this, so I will prepare my data again. So I have to prepare. So X is nothing but you can say 1 by T here. So 1 by T. So second column has the temperature, first column has the concentration. So I'll divide by 1 for all this like for all the elements of the second row, sorry, the second column. And U is also there. U is nothing but log of concentration. So for all the values of column 1, I have to do log. So X is there, U is there. So X is there, U is there, and also K naught is there. Sorry, X is there, U is there. So now I have to find out this A naught. A naught is nothing but L and K naught. E minus E by R is nothing but my A1, and N is nothing but my A2. So y is like again y is here uh, log of r. So that's why log of r or log of y data here because I am taking y data as r. So n is nothing but the length of y. So again I have to prepare first column feature matrix. You can say design matrix or feature matrix, whatever you can say. So earlier we had only one and x, right? So we are here we have one column of ones, and we have column of x, and we have column of u because this is linear in two variables x and y. And then we have y. So if I do this, I'll get the values of a naught, a1, and a3. Okay. So a naught, after I get a naught, again I have to get the value of k naught, right? So if I want to, a naught is equals to ln k naught, which is nothing but k naught is equals to e power a naught. So exp of a naught. A naught is nothing but here phi 1. So e by r is minus e by r is 5 by 2. So we will get this value, and n is nothing but 5 3. So we got all the values of k naught minus e by r and n. So linear regression using this is done. Like we can also do the same thing using the LSQ. So this is the thing. Like here we can also use nonlinear. So earlier we had this thing, right? LSQ curve fit, because this is a nonlinear. Where is that? Yeah. So just say like instead of doing this thing, I can just take this formula only directly, which is R is equals to K naught into e power minus E by RT C power n. So what I can do, like instead of doing this linearization and doing the linear regression, I can do non-linear regression also, because this is a non-linear relationship between R and C and T. So I can use this LSQ non-linear formula. So this is the syntax. Like I have to, here we are finding out the value of phi, and then we have to define the function for which we are doing the nonlinear regression. So this is my where is that thing? RxN function. I think I have defined it. Yeah. So this is the function. Like I have not defined it in a separate file. I have defined it below. Like you can do like this also. Like if you want to define a function, like you know, you don't need to always make a separate file. Like that is a better way. Like making a separate file is better way. But you want to, if you want to make the code like in a single script, you have to write function. Like if you want to write like that, you can use like whatever the functions you define, you have to define at the end of the script. So that's why I'm defining this function at the end of the script. So you can see that here I have k naught, which is phi 1, and e is phi 2, and n is r, and c is my the first variable, and t is my second variable, and I'll have this uh, here. This is e by r. So this is e by r. Like I'll take e by r as e, so it won't make much difference because this is just an, or you can write like this u b r u b r u b r. Yeah, e by r. And I'll take the value of error of this. This function will throw me the value of error between the observed data and the predicted data. R is nothing but the predicted data. Predicted values of y. Predicted values of y. R is nothing but the predicted values of reaction rate. So, and now this LSQ non-lin function will try to reduce this error and find out the values of phi. So find out the values of phi. Phi is nothing but k naught e by r and n. Like whatever the parameters which you have, it will estimate the values of those parameters. So you have to give the value, you have to give the values of x data and y data, and you will also have to give the guess values. Like we should give some kind of initial values per phi. Like then only it will estimate the accurate values. Like you have to initialize it. So if we run this, like we are doing this in two ways. Like first we are uh, linearizing this equation and doing the linear regression, and the second way is like we are directly using nonlinear regression uh, function and doing nonlinear regression. So both should be, both should give me good results. Like now, if you want to find out what are the values of phi you are getting, like here, this is the phi value. Like by doing linear regression, the phi values which I am getting is 2.4 minus 480 and 0.4618. The phi values which I am getting, or the parameters which I am getting uh, using this. Okay, so these are the phi values, but I want k naught value is I'll just clear and do, okay. So k naught is 7.759, e by r is 480, and n is 0.468. Now this phi LSQ will also give me the same thing, because it should give, because the same thing we are doing using two different methods. One is linear regression and one is nonlinear regression. So phi LSQ will give me this. So now you can see these values are not exactly matching, but these are very near to each other. So k naught here is 8.5, here it is 7.75, here it is 8.5647, and here E by R is 480, and here it is 493, and this is n is 0.1468, and here it is 1.0.14. So linear regression and non-linear regression are done, but like they are giving like very near values, but like they are not giving the same exact values. So like curve fitting is being done here, first using the linear regression, and then we are doing the curve fitting using the non-linear regression. So two methods of doing regression are explored here, linear and non-linear regression. So if we are getting, yeah. So this should be wrong because the data prepared was wrong here. The whatever the thing which is given here is wrong in the lecture. The values are wrong. Okay.
Sir,
Yeah.
can you just go to the line number 51?
Line number 51 of this code. Yeah.
Yes, yes, yeah.
Yeah.
What is the
Hmm.
significance of this line, sir? Because we are taking the difference of y data, nothing but the input, and we have
Y,
calculated r. Y
hmm.
data is the input, am I right?
Y data
Whatever the
is the measured value of y.
yeah, that's what we are giving y values. We are calling the
Y,
function and we are giving the input values, and
yeah.
r we are computing. So and we are
This
taking
is
as some
nothing
error.
but error. Error. This is
Also
the
error
measured
of the
value.
uh,
Error of the measured value minus the predicted value. So
okay.
now you can this t this relationship is predicting the values of y for the given x values. Okay, but we have already measured this value of y data, right?
Yeah, clear, sir, clear.
Yeah, yeah,
Excuse me, sir.
yeah, yeah.
Sir, is there any rule to set the initial guess values?
Yeah, you can take any values. It's not uh, like, but these functions are very sensitive to this initial values because uh, like 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 let's say if you are working in chemistry or chemical engineering, you will always have some feeling about these values. Like you will have some guess, like okay, this value will be near to 1, and this value will be near to 100, and this value will be near to 1. So based on that you can just give those values. Okay, you will have
Sir,
some. Mm,
huh, but sir, sometimes this least square non-line function stops the working.
stopped
I
working.
got the error like this. It stopped because the final change in the sum of the squares relative to its initial value is less than the value of the function tolerance.
Function tolerance. Okay, okay.
Uh,
Uh,
so local minimum possible. That type of message I received.
okay. So maybe like you solved which problem? Like
That graded problem, I think it is the third one.
graded problem.
Mhm.
I think you they might have given this given you the initial values, right? Like initial guess.
Initial guess is not given, but I taken it according to my choice.
Okay. You have taken it.
I set it.
Okay. We'll see.
That module 9
Graded, right?
graded.
Which one?
The third one.
Third one. Oh,
Third one.
okay,
Yes.
okay. So the thing is like they should have given you this initial guess. Otherwise, this this function will like throw out some error. Like if the initial guess is not correct, then some
Uh,
kind of error will be happening.
Sir, I have tried by taking initial guess differently, but output is very varies according to the initial guesses.
Okay, okay. Output is
Every
like
time
that.
it gives different values.
Yeah, yeah, yeah. Obviously, it will give different values. You won't get same thing. So I think uh, C and so others are getting this problem. Have you solved like any of the other people who have done? Nasir, have you done this problem?
No, sir, to solve, sir. To should complete.
You have not completed.
Not it. This time it was with
Okay.
busy schedule. I'll do it today.
Yeah, we'll try to do it. Okay. The other thing which you can do is
Sir,
uh,
I have converted that relation in linear form and it is working fine in linear form by taking reciprocals both sides.
mm, mm, yeah. So you are not getting this in this nonlinear, right? Nonlinear
Non-linear,
form.
the answers are not matching with the linear form that I have received the answers as an
Okay.
output.
So, but the thing like I can give one. Okay. So you might have got these values, right? Like alpha not
Yes, yes.
alpha one,
In
alpha two,
problem,
alpha three.
yes,
Yeah.
all the values I have obtained,
Yeah.
but in
The
using
here,
the
so I'll like what you can do is like this like whatever the values which you got here, you can take as you can take them as initial guess in the nonlinear regression. That you can do.
okay, 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 okay,
Maybe
correct.
then you can get something. Or let's say we'll just try to solve this. 0.5, 1.5. C is 0.95. In exam, if you don't get these initial values, you will get full marks because that has to be specified. Otherwise, your answers very poor.
Sir, only check once lines 7 and 9, no? I
Mm-hmm.
think 7 and 9 line number. I
Yeah, what
think
is it?
all should be 7 and 9 line
Mm.
number. I think all in the
Oh,
data I
this is
see.
CCC. Okay, okay, sorry.
Yeah, that is all.
This is that. And we have we'll take X as C and we'll take U as 1 by start has to be. Yeah, is 1 by R. No, it's nothing but K1 by K max. Alpha 1 is 1 by K max. 1 by K max. This cannot be written like this. 1 by just giving some names. This is my A2 by K max. Okay. So from this, get K max is equals to, or I can just directly give here only. K max is equals to 1 by 5 2 and A2 is equals to KB max into K max. K1 is AB max into K. Let's solve till here. AB max. Should not have clearance. What is the value of K1 which you got? K2, K. Are these the values which you got? Who was asked? Who asked?
Yes, sir. I'm checking it.
Okay.
Sir, I obtained K1 as 0.1588.
0.188.
And K2 is 0.0176.
Okay. Yeah. I think I'll check. We'll do this non-linear also. Then we will check it. So I'll take this pi as I'll take this as 10. Take this as some 10, 50, and 100. That will be my initial guess. And A naught is my K max. This is my K1. This is my K2. These things are not required because already I have. A max into E 1 plus A1 will make it into transpose. transpose A2 into B transpose. Y data is equal to R transpose. It's just confusing. Take that out. Let's run this. Okay, I have to change this. Run whole thing. Uh, okay. A2. This has to be like this. Okay.
Sir, same type of message I have received in this example.
Oh, then it is like then the problem is solved. This is not error. Okay.
Okay, but while
Mm,
we changing the initial guesses, the
mm.
answers varies accordingly.
Yeah, yeah. So I'll just check what we have got here. I'll just check. Okay. We have got A1, K max as 1.2318. This is 0 and this is 0. Oh, okay. Local minimums found. Here we have got K max as no, no. Initial values I have to give properly. What was the K max which we got? 116. K1 9.0. K2 we got 56. So I'll give 100. Initial value as 100. 9, 10, and 50. And also we are getting same thing. Okay. I'm not simple. Okay, I'll do one thing. Num is equals to K max T transpose. I think we are doing give me some. Is K max 1 by 2 T square minus 1 by R is K1 by K, no? K2 by K. Okay. K2 by K max. C 1 by K. So now choose L1. This is wrong. K2 by K max is 5 2. And 5 3 is 1 by K. 1 by K. I think you get some. A max is this. A1 is this. A2 is this.
Yes, sir. These are
Hmm.
the values that I also obtained.
Oh, then okay. Then I'll put this as 0.1. Then I'll take this as 0. See, run it again. And I will let's be just showing some. I don't know. Okay. What, let's think now we are getting near. A max is 2. Yeah. A1 is this. A2 is this. We are getting. Yeah. So there was the confusion. Okay, this, if you take like this, your initial values near to this, whatever you have obtained, you will get these values.
Yes, sir. Correct.
Something goes wrong and everything will mess up. So I had taken transpose here, which should not have been done. C I have to take directly. I don't know what the difference it makes, but yeah. Let's see. E is this E by dot C. Give me one. C transpose dot C. Where is this? Okay. A little bit of here and there, everything will get messed up. Okay. Think this is clear, right?
Yes, sir.
Okay.
It's fine.
Anybody else have any question? I think interpolation is simple. You just have to use the formula. So I think you have watched the lecture. So this regression is a little bit tricky part. So do this carefully, like do linear and also compare your answers with non-linear. So that will be, I think, the 2 cents which I'll give. Let's see if I take 111 as my initial conditions, what it will do. Yeah, then also it is giving a good answer. Say if I take 0, 0. So it is giving. So if you take 10, 10, 10, then also it is giving. If you take 100 also it is giving. So it's, so initial condition is not sensitive. So this is not initial condition sensitive, I think. Okay. I think
Yes,
Bhavesh, you
sir.
have to check your code.
Okay. I need to verify my code.
Yeah, yeah.
Okay, sir. Okay, thank you,
Okay.
sir.
Okay, okay. So today we'll stop it here. Okay, guys. If you have any doubts, you can ask me. We'll clear those.
Excuse
Otherwise,
me, sir.
we'll stop. Yeah,
Can
yeah.
you just show the code, sir? Once finish the code with elaborated one.
This one,
Yeah, yeah, elaborated one.
the large,
Then,
like
yeah, enlarge.
entire thing.
No, no, no. The last one which you have did, no? We had a
This one.
confusion about yes, yes. Can you
Yeah.
enlarge, please?
Okay. It's fine.
And the above one. I think the above one, no, we had.
Hmm?
I think we had this one and above one, right, sir? Discussion, no? This one. Is
This
this
one
one?
also. Huh?
We had this discussion.
Yeah, yeah. This one.
This one we
This was
have.
the this is the reaction thing which we did. The Arrhenius reaction.
Now for the
This now we solved this assignment problem, the fourth one.
okay.
Entire
Can you
thing using non-linear and linear least squares.
yes, can you just show the linear parts? Linear.
Linear. Yeah.
This is linear.
I'll just upload this. You can just check.
Okay.
You can go to this Google Drive and download this. Yeah.
Just in doubt was why C transpose is taken, sir.
Hmm?
And next code, the below code,
Hmm.
why C transpose is taken?
Oh, I
Line
have
number
removed it.
above.
Removed it.
Not
Hmm?
here, not here. Above. Yeah, here. Line number 21.
Yeah, yeah. Because uh, this is a row matrix, right?
Okay.
I want to convert it into a column matrix. I want all these into a columns. I want all these to be columns.
Okay. Then just enlarge this code. I will just take a pic. The above one and the below one. The above one also. Above one.
Above.
Ah, yes, this one. Yeah. Thank you.
Uh, chalo.
Yeah. Super. Thank you.
Any other doubts, guys? No. No doubts. Okay. Okay. Thank you, everyone. Thanks for joining. Question number 2, Abhishek, you are asking something. Abhishek left. Okay. Okay. Thank you, Nasir. Thanks.
Thank you, sir.